Hello, today we'll be having a look at this equation involving integers x, y, and z and finding all non-negative integer solutions to the equation x cubed plus 2y cubed equals 4z cubed. Okay, so this is quite interesting because there's three variables, all non-negative integers. So you may think there's quite a lot of solutions because there's three different variables and we can make x, y, z anything we like. But let's have a look at what the solutions will be. The obvious solution is if x, y, and z are all equal to 0, because the left-hand side will equal 0 cubed plus 2 times 0 cubed, which is 0. The right-hand side will equal 4 times 0 cubed equals 0. So x, y, z equals 0, 0, 0 is a valid solution. But the question is there any other solutions? You could try substituting different values for x and y and seeing if the right-hand side is 4 times a cubed number. So you could experiment with different values of x and y and see if you can find any other solutions. In fact, it turns out there are no other solutions. And to prove there is no other solutions, we'll use a technique called Fermat's principle of infinite descent. So when we're doing Fermat's principle of infinite descent, we assume a solution exists, a non-zero solution exists, and then we try to construct a even smaller non-zero solution using that. And the idea is that you can't create smaller and smaller solutions forever. So since we can't create smaller and smaller solutions forever, it means our initial assumption that there was a non-zero solution is wrong, and we get a contradiction. So this will prove there are no other solutions. To see how Fermat's principle works, we can assume a solution xyz exists where x plus y plus z is minimal. So minimal means assume, this should say a non-zero solution. So assume a non-zero solution xyz exists where x plus y plus z is as small as possible. So we want to find the solution, the non-zero solution with the smallest possible sum of x plus y plus z. And since this is a non-zero solution, we know in this minimal solution, x plus y plus z will be greater than 0. Okay. If we have a look at the original equation, we can see 2y cubed is even and 4z cubed is also even. So this number x cubed must also be even, because in order for something plus an even number to be even, this number has to be even. Since x cubed is even, it wouldn't work if x was odd, because if you take the cube of an odd number, it is still odd. So x itself must also be even. So x is even. And since x is even, we can write x as equal to 2a, where x we can write as 2a, where a is a non-negative integer. So now if we substitute x equals 2a, we'll have 2a cubed plus 2y cubed equals 4z cubed. So now 8a cubed plus 2y cubed equals 4z cubed, and divide both sides by 2. 4a cubed plus y cubed equals 2z cubed. Okay, now we have this equation involving a, y, and z. We can also see here we have an even number 4a cubed, an even number 2z cubed, which means y cubed must also be even. And since y cubed is even, just like what we did earlier, we also know y must be even. And since y is even, it means y can be written as 2b, where b is a non-negative integer. Okay, and if we substitute y equals 2b, we have 4a cubed plus 2b all cubed equals 2z cubed. And now we can rewrite it as 8b cubed equals 2z cubed. Now we divide both sides by 2, and we have this. Okay, the final thing we'll do is see, or the final set of steps to solve this question. We will see 2a cubed and 4b cubed are even, and even plus even will mean z cubed is even. And again, since z cubed is even, we must have z is even. Since z is even, we can write z as equal to 2c, where c is a non-negative integer. And if we substitute the value of z equals 2c, we have 2c cubed. And this is the same as saying 8 of c cubed. And divide both sides by 2 again. Okay, we have a cubed plus 2b cubed equals 4c cubed. So this is actually this is the exact same as this equation, except x, y, z is replaced by a, b, c. So we have the solution a, b, c. And remember a, b, c, since we had x equals 2a and y equals 2b and z equals 2c, a, b, c is the same as x over 2, y over 2, and z over 2. And now remember the minimal solution. Remember x, y, z was a minimal solution, which we assumed the minimal non-zero solution. However, this solution over here, if we add up a plus b plus c, we have x over 2 plus y over 2 plus z over 2. This is equal to x plus y plus z over 2. And this is in fact less than the sum of x plus y plus z. And this is also because x plus y plus z is greater than 0. So since x plus y plus z is greater than 0, we in fact have a plus b plus c is less than x plus y plus z. And this is bad because we assumed x, y, z was the minimal solution, but now we have this a, b, c solution, which is even smaller than x, y, z. So it means our initial assumption was wrong. And it turns out using infinite descent, we have a contradiction because we can't have something smaller than the smallest solution. So it turns out the initial assumption was wrong. And there is, by contradiction, there are no other solutions apart from 0, 0, 0. Using Fermat's principle of infinite descent, it turns out there are no other solutions apart from just 0, 0, 0. Okay, so that ends the proof for this question using Fermat's principle of infinite descent. Hope you enjoyed the video. Thanks for watching, and I'll see you in the next video.